By age 65, a competitive endurance athlete is subjecting their body to intense, continuous mechanical stress to maintain their performance. But behind that cardiovascular stamina lies a gradual biological change, sarcopenia. This is the progressive, age-related loss of skeletal muscle mass and functional strength that accelerates after the sixth decade. Logging high-volume miles on the bike or the trail forces the heart and lungs to adapt, but it does not stop the specific breakdown of the contractile tissue driving the pedals. Without intervention to preserve that muscle, the loss of skeletal mass eventually compromises both systemic metabolic health and the functional independence required for high-level training. The mechanism regulating muscle repair lives within our cells, governed by a signaling pathway known as mTORC1. In a younger body, this pathway acts as a highly sensitive responder. A modest dose of protein easily initiates the protein synthesis required to rebuild damaged tissue. This molecular comparison reveals a stark difference as we age. On the left, the young muscle pathway is clear and responsive. On the right, the older muscle exhibits anabolic resistance, where the cellular sensors for amino acids become severely desensitized. If we introduce a standard 20-gram meal into both environments, the young pathway responds immediately. In the older muscle, that same input fails to reach the threshold required to initiate repair. While increasing protein intake can force this pathway to activate, chronic, unremitting mTORC1 signaling is associated with accelerated cellular aging and the progression of certain malignancies. The master athlete must find a way to reconcile the need for acute muscle repair signals with the long-term risks of sustained growth signaling. Longitudinal data from the NHANES 3 study tracked the relationship between protein intake and mortality in human populations over an 18-year period. Under age 65, high protein intake correlates with increased cancer and overall mortality risk. But past age 65, the trend reverses. High protein intake is associated with reduced mortality, while low protein diets correlate with higher risk. In older demographics, the immediate risks of frailty, immune dysfunction, and muscle wasting outweigh the potential dangers of moderate growth signaling. For the master athlete, maintaining adequate protein to sustain muscle mass functions as a protective strategy against age-related decline. To prevent chronic muscle catabolism, a master endurance athlete requires an intake of 1.5 to 1.6 grams of protein per kilogram of body weight. For a 170-pound competitor, that means a daily requirement of roughly 120 grams of total protein. But total daily intake is only one variable. If the concentration in a single meal fails to reach the threshold of anabolic resistance, the repair process remains inactive. This molecular scale measures L-leucine, the amino acid that triggers repair. Overcoming age-related resistance requires a single meal dose of 3 to 4 grams of leucine. Reaching that threshold takes 40 grams of high-quality protein to initiate muscle synthesis. Dividing the 120-gram daily requirement into 3 of these 40-gram portions allows the athlete to meet their daily total while ensuring each meal successfully restarts the synthesis process. Supporting aging muscle is a matter of meeting these specific concentration thresholds at the per-meal level. Concentrated protein intake does interact with the cardiovascular system. Research has identified a signaling threshold where high protein levels can activate certain immune cells. In experimental models, when protein levels exceed 25 grams per meal, they trigger macrophage signaling linked to the progression of arterial plaque. Endurance athletes have a unique physiological defense: exercise. Physical activity increases the sensitivity of muscle tissue, allowing it to rapidly clear amino acids from the blood for immediate structural repair. The choice of protein source further modulates this risk. Plant-based proteins generally have slower digestion kinetics compared to rapidly absorbed animal isolates like whey. Slower digestion extends the delivery of amino acids into the circulation, avoiding a sharp spike and maintaining a more moderate exposure for the cardiovascular system. By managing the rate of nutrient delivery, the athlete can trigger muscle repair while minimizing the signaling thresholds associated with vascular risk. The resulting protocol focuses on 3 to 4 daily meals, each delivering 40 grams of slow-absorbing plant-forward protein. As this profile shows, fortifying pea protein with free-form L-leucine allows for an anabolic response comparable to animal sources while maintaining a cardioprotective dietary matrix. These precise doses are only effective if total energy intake is sufficient. Chronic low energy availability impairs recovery regardless of protein timing. Furthermore, protein intake requires the mechanical stimulus of resistance training to effectively signal the body to maintain skeletal muscle mass. Long-term health also depends on monitoring micronutrients often limited in plant-heavy diets, specifically vitamin B12, adequate dietary iron, vitamin D, and omega-3s. This protocol is a system of interdependent variables, each required to maintain the athlete's structural integrity over time. Standard guidance for aging often emphasizes reducing intake and activity to lower disease risk, a strategy that does not account for the metabolic demands of a competitive athlete. For those over 65, this calibrated nutritional approach supports the muscle mass and functional capacity required for high-level endurance performance. Mastering the trade-off between skeletal muscle repair and cellular maintenance allows for the preservation of high-level endurance performance throughout the aging process.